So now we're doing a titration of a weak acid and a strong base. Notice that I've got the same numbers as before. I didn't want to change it, but I do have I have an actual Ka value, because I did change the acid to make it a weak one. So again, it's still just that idea. I've got an acid, a weak acid in there, and I'm going to put an AOH into there. So that's not any different. It's just that this time the acid won't break apart completely. Only a little percentage of it is going to break apart into H pluses, which is how we get our pH. So when you haven't added any NaOH at all, we're just looking at just that formic acid stuff right there, that HCO2H. And so we can just do a normal ice chart. I know before you could use that pH thing, but now we've got to use an ice chart. And so we've got HCO2 minus, and then we have Ka, and I already have that value from the problem. And then we're going to plug in an initial amount. Now, in this case, the volume isn't going to matter. It's just the molarity. It doesn't matter if I have a little bit or a lot of it. It's always going to be the same pH as long as I'm not changing the molarity. I just got my ice chart, and I'm just going to be plugging in, my x squared and my 0.4. So this should all be super familiar by this point. You should be super comfortable with what you're doing. So I'm just going to get that E equation in there, multiply it times your 0.4. I need to take the square root of it. So there we go. There's my X. So remember, X is at H3O plus, and, 84585. And then remember, I've got to do the negative log of that number to get my pH. Sometimes I'll just do it like that and put negative log and just put an arrow up to it. And then when I plug it in, negative log of the answer, that gives me my pH right there, my 2.07. So that's the first step. So that's nothing new. That's all the same. Since these are the same numbers as that strong acid, strong base, I'm not going to recalculate the moles. I'm just going to copy and paste it from earlier. All right, so these are just the copied over values from before that I had done in the previous problem, except that I'm changing my acid because I have a different acid here. And then I've got my base amount. So these are my moles of each of those. So I can use those in my ICF chart and then go ahead and do my calculations with my buffer after that. So I need the equation. I need to write out my acid plus my base. And then I'm going to lose the H and the OH. They're going to make water. And my Na is going to take the place of that H I lost. Again, like I said, that Na just replaces the H location. So I'm going to set this up as an ICF chart. Initially, and I'm getting these numbers again from that volume times the molarity. I've got them just to the left over there. 0 and 0 on the products. Now my change, look for the smaller one. This is the big one. The smaller one is that 0.01 value. That's the one that gets subtracted from everyone. Well, on the left, and then added on the right. And then on the right, plus the 0.01. And the water doesn't matter. So I've got 0.004, I've got none. So my limiting reagent in this one was my NaOH. And you can see I made a buffer because I have a salt and I have a weak acid. Now, I can do my ice chart, or I can just use that handy-dandy Henderson-Hasselbalch equation, which I think is what I'm going to do. Now, remember, it would be divided by a certain total amount of liters, except that for buffers, because I always put them on top of each other, my liter amount cancels out. You're going to see an example coming up, though, where we really have to make sure we put that difference in there. So pH equals pKa plus the log of that number. I'm just using L to hold the place, just to remind you that we're doing it. Notice there's a salt over my acid, and my liters cancel. And now I just need to put it in my calculator, but I need to make sure I've got my pKa. There it is. It's up there. So the pKa, I'm going to rewrite this. It's a negative log of 1.8 times 10 to the minus 4th plus all that other stuff above. I'm just going to simplify it to 0.001 over 0.004. All right. Let's just fill everything in the calculator. So negative log of 1.8 e to the minus 4 plus the log of parentheses 0.001 divided by 0.004 And that gives me 3.142. And that makes sense because my pH is increasing. It was initially like that 2 number, and now it's at that 3-ish number. Like before, I'm going to copy in those mole values. Okay, so you can notice I've got an equal mole amount of both of them, so that implies that all of my H's and my OH's are all accounted for, and they're all paired up, and I don't have anything extra. And when we do the ICF chart, we do still want to do it because we are still making product. Just because the reactants are completely used up equally, we still are going to be making a product. So HClO2 plus the NaOH, and I'm making same thing I made earlier, the HCO2 Na plus the water ICE. Final, sorry, not E. And then I've got 0.14, 0.014, 0, and 0, because initially I don't have any. I'm going to subtract out my, that's my salt. I'm going to subtract out my 0.014 and my 0.014, and I'm going to gain it on the right-hand side. Notice at equilibrium, I still have a salt. Now, you remember salts. We can find pHs of salt as long as they're soluble, and this is a soluble salt. The Na part doesn't matter, but the HClO does. So I'm going to set up a ice chart for this one. Remember, with these salts, it's like you end up with the opposite K of what you intend to have. So there's my salt part that matters, plus my water. So I'm going to add it, H2CO2, HCO2 plus that. So that's a Kb, but remember, I've only got a Ka. All right, so I'm going to say my Kb is equal to my Kw over my Ka, and my Ka value is earlier on the page. Remember, that's 1 times 10 to the minus 14th over that 1.8 times 10 to the minus 4. And that's going to be equal to my base times my acid. I'm barely squeezing in here, but that's going to be x squared is what that's going to be, over my HCO2 minus. I'm going to scooch this over so I've got a little bit more room. I'm just reminding that that's how much of that salt that I made. So that's my initial amount. Those are my x's. So I've got x squared over the 1.014 minus x, but I can throw the x out. Now, here's where it matters. You see how I drew that line? That's because it has to be in here in molarity. And I know I've been throwing out the total liters, but that only works when I do buffers. So here's my total volume right there. It's 115. And I did this in the acid strong base where I added the two together. The 70 milliliters plus the 35. And then we're going to bring that over. Now what I'm going to do is I'm just going to basically cross multiply up that fraction, and then I'll take the square root of it. Remember, I'm going to solve for my x, that's what OH is, that'll be POH, and then I'll do 14 minus POH to get to my pH value. That's kind of where I'm going with this. And oops, I forgot. So I'm going to make that a positive number, even though I forgot the negative in there. So you can tell that I've got my pH is 8.415, and that makes sense because I'm past the equivalence point, and that's a little bit more than 7, so that makes sense. let's go to our very last section right here. This is past equilibrium. This is the easiest point of the whole problem. And I'm not sure why I have a 41. It should be 80. So I'm going to copy in the entire earlier problem that I did with the strong acids, strong bases. So you can see I've just changing my acid here to that HCO2H, and I'm going to change my little reaction here. But I've got these same amounts, and the interesting thing is that once I get past the acid, it's really the base that prevails. So as long as I know how much base was used up to begin with, you can see I've got the 0.02, and then I have to turn it into molarity. But that's the problem right there. You can see I don't have any acid left, so it's just the base. So you might be wondering a little bit about, well, what about the fact that we really did make something over here? All right, so let's take a quick look. We have this quantity here, which is that 0.002 divided by the 0.115. I'm going to write that number down over here. 0.002 divided by 0.115. And that gives me 0.01739. So that's how many moles of OH that strong acid, this NaOH, is giving me, all right? So that's what's going to go in the pH equation. It's what ends up going in there. So if you're wondering, well, how about this little guy? What about if he does, you know, didn't we just deal with this up here? Well, we did deal with this up here, right up here. And the reason we dealt with it was because we had made that salt and there was nothing else in there. Now, basically what I've got is a really strong base in there with just something that's a tiny salt. So you'll notice when we did this problem, we ended up with this concentration of X. So that's like saying this is the strong. And then if I add in that tiny concentration, 1, 2, 3, 4, 5, 2, 6 more moles of OH could be generated in that case. 1, 2, 3, 4, 5, 6. Yeah. So when you compare the two, this one's amount is negligible compared to how much of the strong that there is.